Okay, so in lecture 3 we were talking about kinematics, and we just didn't quite get to go over two-dimensional kinematics very carefully. That's not too bad, because two-dimensional kinematics is really just kinematics in each direction separately. So you can treat components that are perpendicular to each other as completely independent. So if you, for example, have the ground, and you have conventional coordinates that the y direction points up and the x direction points to the right. Let's see what happens to the equations for the position in each direction. So what we have to do is figure out what's the acceleration in the x direction and what's the acceleration in the y direction. So from our picture here, we know that the acceleration of gravity pulls down. So the acceleration in the y direction is going to be equal to minus g. And what's the acceleration in the x direction? Well, there are no forces acting in the x direction, so that acceleration is just 0. So if we plug these two things into these equations, in the x direction we're going to get this term canceling because, or not canceling, this term is 0 because ax is 0. So x will be x naught plus v naught x times t. And in the y direction, we're going to have all these terms, but ay is going to be equal to negative g. So we'll get y naught plus v naught y times t minus 1/2 g t squared. So let's try a problem on two-dimensional kinematics. So here you're supposed to be serving a tennis ball by hitting it totally horizontally at this height and with an initial speed v naught. And it says the ball must clear the net, so this is the net, at a height of 0.9 meters, and it's a distance of 15 meters away. And we want to calculate the minimum speed required for the ball to clear the net. So what does minimum speed mean? Well, if you hit this ball really hard, then it would shoot out something like this. So that cleared the net with quite a bit of clearance. We want to find the velocity where the ball just barely clears the net, so where the final position at the net is just above the net. So all this minimum speed business is telling us is that this is the final position of the ball, and this is the initial position. So I think it's wise to start these problems by just writing down everything you know. So in this case, let's just start with the x positions. So the initial x position is 0 if we set up our coordinate axes correctly. So let's put the origin right here, and this is the y direction, and this is the x direction. So initially, the ball is at x equals 0, and at the final position, the ball is at d. Okay, so how about y? Y initial is hb, and y final is the height of the net. How about velocities? So we need the initial velocity in the x direction and the y direction, and the final velocity in the x direction and the y direction. So the initial velocity in the x direction is v naught, and it says that it's hit horizontally, which means that there's no velocity in the y direction. At the final position, the x velocity is going to be the same. How do I know that? I know that because the acceleration in the x direction is 0, and the acceleration in the y direction is minus g. So if there's no acceleration in the x direction, the velocity can't change. So this is just going to stay v naught. And we don't know the final y velocity. So what can we need? This seems kind of hard. What is the thing that connects the x position with the y position? Well, if you look at the equations we wrote on the previous page, the thing that connects them is the parameter t. So time at the same time, you have an x coordinate and a y coordinate. For every t, there's an x and there's a y. So that's the parameter that links the two directions together. So here, let's, I think we can figure out the time it takes for the ball to get from this height to this height. So you can think about this as just a ball falling and a ball moving to the right. And it's like sort of the combination of those two things. So let's figure out how long it takes the ball to fall if we just dropped it in free fall, to fall from here to this height. So we're going to use the x direction to get a time. Or sorry, the y direction to get a time. So we're asking basically the question, how long does it take to get or to fall from a height of HB to a height of H net? Okay, so the final y position is the initial y position plus v naught yt minus 1/2 gt squared. Now the initial y velocity is 0, so this goes to 0, and then we can rearrange this. We have y final equals, y final minus y initial is minus 1/2 gt squared. And now we know what y final is. Y final is hn, and the initial is hb, and that's minus 1/2 gt squared. So now we just have to solve this equation for t. So let's see, if we put t squared over here, then we're going to have 2. There's a minus sign, so we flip these. Divide by g. And then let's just take the square root also. Okay, so let's just check to make sure this makes sense. So we're going to have to take hb and subtract hn. And I hope that that's a positive number because we're going to take the square root and get a time, and we don't want it to be imaginary. So hb is bigger than hn, so this looks good. So now we're going to use this time to figure out v naught, because we know that in the time it takes the ball to fall from this spot to this spot, the ball has moved in the x direction from this value to this value. So it's gone a distance in the x direction of d. So we'll use t to figure out v naught. So the final x position is the initial x position plus the velocity in the x direction times t. Oh dear, sorry. So we solve for v naught. So v naught is going to be xf minus xi over t, and xf minus xi is the distance divided by time. And now we're just going to take t and plug it in here. So that gives d times g over 2 hb minus hn, and you take the square root.